Welcome. So today we are going to continue on through Unit 2, and we're going to start our discussion of Chapter 6. So in this chapter, we're going to be working with the composition of these chemicals that we've been exploring. So in the last two chapters, we've learned more about elements and compounds, and now we want to look more about how do we work with these. And, one of the important facts that we'll get there is how to quantify the amounts of elements in compounds. In other words, how do we count it? How do we quantify how much we have, right? And so we're going to get into some of the topics dealing with how we do this. Now, a couple of the points that we need to really understand at the beginning is we don't ever deal with single molecules or single atoms, right, of elements and compounds, right? We deal with large amounts, large numbers of atoms if we're dealing with elements, or molecules if we're dealing with compounds, or formula units, etc., right? So we're dealing with large amounts, right? Because remember, these individual atoms, molecules are tiny, tiny, tiny. So even a very small sample of an element or compound contains many, many, many atoms or molecules or formula units. So we have to have a way to count them, to quantify them. Now, the technique we use is something that can sort of generically be referred to as counting atoms by mass. So, in other words, we're going to express them in quantities, right? Quantities in grams. So how do we go about doing that? Well, unfortunately, we can't just count them, right? So that would take, an unimaginable amount of time to count even a small amount of atoms and molecules, and besides the fact we can't see them. So, a lot of times when we have very large amounts of something, we use what we call a counting unit. And so, a counting unit would be something like a dozen, or pairs, or some other unit that stands for a certain number of individual items. So when we're working with atoms and molecules, our counting unit is the mole. Now, this will be abbreviated MOL when we write it as a unit, but the mole will become our friend, right? So what is a mole? Well, 1 mole is equal to 6.022 times 10 to the 23 items, right? So it's a unit, right? A counting unit. So the units of it are going to be whatever we're counting, right? Are they hydrogen atoms? Are they, water molecules, etc., right? So, but 1 mole of any of them always has 6.022 times 10 to the 23rd individual items. Just like anytime we have a dozen of something, it always has 12 items. So this is a huge number of items, right? But we need a unit that big because we're going to be dealing with such large numbers of items, of atoms and molecules. Now, we might be wondering where this number came from, and it doesn't just pop out of a hat, right? It is based on mass, right? And specifically, this equals the number of atoms, more specifically the number of carbon atoms, right? Because that's what we're going to be talking about. The number of carbon atoms in exactly 12 grams of the pure carbon-12 isotope. So remember our isotopic notation, right? So if I have exactly 12 grams of carbon-12 isotope, it contains exactly this number of atoms. 6.022 times 10 to the 23rd carbon atoms. And this is where this where this unit comes from. So everything is based around carbon 12. So this is one of the reasons why we call it counting by mass, because this ultimately is a mass-based system, right? We took a mass of carbon 12, the exact number of atoms that are in there, right, became our counting unit. Now, you might also hear this referred to as Avogadro's number. Right? That's another term that we use for the mole. So if you hear that term Avogadro's number, they're talking about 6.022 times 10 to the 23rd. It's the same thing. Okay. So first big thing here is we really have to understand this concept of the mole and what a mole is. Now, this allows us to count atoms, right? So Avogadro's number is a conversion factor, right? It tells us how many items are in 1 mole, right? Just like, any other conversion factor where, tells us that there's 12 inches in a foot or 2.54 centimeters in an inch, etc., right? So it's a conversion factor. It allows us to convert between a mole and individual items. So we have this counting unit, this conversion factor that allows us to move between moles and individual items. Now, the next step will be to figure out how do we express the number of moles as grams. Now, we'll get to that in a few minutes. But before we do that, I want to do a couple of practice calculations just so you can see how this all works. So, I'll show you a sample one here where I have 3.5 moles of helium, right? And I want to know how many atoms of helium that contains. Well, I know that every 1 mole contains 6.022 times 10 to the 23rd helium atoms, right? So notice dimensional analysis, right? We're following the units, right? So I'm going to make sure, because I'm starting with moles, that the moles part of my conversion factor is on the bottom so that it cancels out. And so the unit that I'm trying to achieve, right, the helium atoms, is on top. So if I do my math, 3.5 times 6.022 times 10 to the 23rd divided by 1 gives me 2.1 times 10 to the 24 helium atoms. Okay? So that's the idea, right? It's just another conversion factor. It just allows us to go from moles of a certain material to atoms, to individual items of a certain material. So let's look at this question about gold atoms. So it says I have 8.83 times 10 to the minus second moles of gold. And I want to know how many individual atoms that I have. So the key is I want to go from moles to atoms, right? That's how I know that I'm going to use Avogadro's number, right? Because anytime I want to move between moles and atoms, or moles and molecules, or moles and, anything other than grams, I'm going to have to use Avogadro's number. So, now, multiplying or dividing, how do I know? Well, we follow the units, right? So, we know that the conversion factor, right, is 6.022 times 10 to the 23rd individual items per mole. So, we have moles here, so we need moles down here. And we're trying to get to AU atoms. So that's going to go on the top. And so we have 1 mole, 6.022 times 10 to the 23rd individual atoms. So our moles cancel out, right? So we're going to be left with units of gold atoms. So if I do my math, I get 5.317, etc. on your calculator times 10 to the 22nd gold atoms. Now, we can't forget about significant figures. So the significant figures, we're going to look at our original number here of moles. In this case, we had 3 significant figures. So we're going to round to 3. So 5.32 times 10 to the 22nd gold atoms. So that's the idea. Now, this allows us to go both directions, of course, just like any convergent factor. So what if I have a number of atoms and I want to figure out how many moles that I have? So in this case, we're dealing with copper. So if I start out with 1.5 times 10 to the 22nd copper atoms, and I'm trying to find moles, right? So how do I want to set up my units? Well, I need copper atoms down here because I want it to cancel, and moles of copper up here because that's what I'm trying to find. So remember, it's 1 mole, 6.022 times 10 to the 23rd individual atoms. My units cancel, right? My copper atoms cancel here and here. So I'm going to be left with moles of copper. So if you put them in your calculator, rounding to this case 2 significant figures, I get quick there, 0.025 moles of copper. Or you could write this as 2.5 times 10 to the minus second moles of copper, if you want to put it in scientific notation. So this is how we're going to use this mole, this counting unit of Avogadro's number, to express a large number of individual atoms as a relatively smaller number of these moles, right? This counting unit. So now that I have a method to go from individual atoms into moles of atoms, now the next step that I said that I needed a way to convert between moles and mass or grams, right? Because ultimately that's my goal, right? So what I'm going to use here is something known as the molar mass, right? So the molar mass is the mass of 1 mole of atoms of an element. And it's going to be, of course, in units of grams per 1 mole. Right? So it's how many grams, what's the mass of 1 mole, right? So grams per 1 mole. So this is what's called the molar mass of an element. Now, an element's molar mass, right, and again in units of grams per mole, is numerically equal to its atomic mass in AMUs. Now, notice the only thing different here is the units, right? The nice thing about this concept of molar mass and the concept of AMUs, our atomic mass, is that numerically they are the same, but they have different units. Now, the reason why this can be done, right, is how these things were developed, right? So both the units of AMU and the concept of the mole of Avogadro's number are both based on carbon-12. And so we have this connection here that allows us to have one number, right, a mass that appears on the periodic table, but it can both represent the mass of a single atom in AMUs and the mass of a mole of atoms in grams per mole. So, for example, if I have 1 mole of sulfur atoms, right, it has a mass of 32.06 grams. Right? Contains 6.022 times 10 to the 23rd atoms of sulfur. Now, that same 1 mole of carbon atoms, right, that same number of carbon atoms has a mass of just 12.01 grams, right? Now, how can the same number of things, right, we have exactly the same number of atoms, they have such different masses? Well, of course, the explanation is not that complicated, right, if we think about it, right? It's the individual atoms have a different mass, right? So every sulfur atom weighs 32.06 AMUs. Every carbon atom only weighs 12.01 AMUs, right? So, of course, if I have the same number of those things, they're not going to weigh the same because the individual items don't weigh the same. Just in the same way, if I were to have 12 grapes and 12 oranges, right, you wouldn't expect these two things to weigh the same, right? Because each orange weighs more than each grape. Of course, 12 oranges are going to weigh more than 12 grapes. So, same idea, right? Because every atom has its own unique atomic mass number, right? Its own atomic mass. Right? Of course, they're also going to differ in their molar masses. So, two big take-homes, right? That number on the periodic table now has two definitions, right? It is the atomic mass, the mass of a single atom in units of AMUs, but it also represents the mass of 1 mole of atoms in units of grams per mole. Second big thing is we can use this molar mass, right, as a way to jump back and forth between how many moles of something we have and how many grams it's going to have. So if I know that each mole weighs a certain amount, then I can go back and forth between how many moles and how many grams I have. So let's do a little practice so that we can see how it works. So let's show want to know the number of moles in 0.58 grams of carbon. So I weighed out 0.58 grams of carbon. I want to know how many moles that represents. Well, if I look on the periodic table and I know that each mole of carbon weighs 12.01 grams, well, I'm going to set up my units so that my grams are on the bottom, so it cancels. So 12 grams per mole. I do my division, and this represents 4.8 times 10 to the minus second moles of copper. So, molar mass allows me to go back and forth between grams and moles. So let's look at a couple of other ones. So let's say that I have 2.78 moles of sulfur. And I want to figure out grams of sulfur. So I know that if I'm going to go from moles to grams, I have to use the molar mass, right? That's the tool. And so in this case, because I'm starting with moles are going to be on the bottom. And that means grams are going to be on the top. And if I look on the periodic table, I would find that sulfur has a molar mass of 32.06 grams per every mole. My moles cancel. I do my math, and retaining 3 significant figures, I get 89.1 grams of sulfur. So 2.78 moles represents 89.1 grams of sulfur. Now, of course, I can combine these two conversion factors that we've just learned, right? We can use the molar mass to go between grams and moles, and then I can use Avogadro's number to go between moles and individual atoms, right? So we can't do it all at once, but I can go all the way from knowing a mass of a particular element to how many individual atoms that represents, or vice versa, by just simply doing both of these conversions. So 16.02 grams of aluminum. Now, the key thing is to remember we have to do it in 2 steps, right? So I know I can go from grams to moles using the molar mass. So in this case, because I have grams, the grams are going to go on the bottom. So if I look up aluminum on the periodic table, I find that it weighs 26.98 grams in every mole. My grams cancel out here, and I would be left with moles of aluminum if I were to do this calculation. Now, we could get an answer there, and you'd come up with something like half a mole, right? A little bit different, but you can get an answer there, or we can just continue on and convert my moles, right, moles on the bottom, into aluminum atoms. I mean that there are 6.022 times 10 to the 23rd aluminum atoms per every mole. Again, my units cancel, my moles cancel top to bottom in dimensional analysis, and I should be left with aluminum atoms as my unit, as the way I want it. So I'm going to do my math, and I'm going to end up with 3.62, so 3 significant figures based on my original number, times 10 to the 23rd aluminum atoms. And so we can say that the 16.02 grams represents 3.62 times 10 to the 23rd aluminum atoms. Okay? So this is the 2 sort of key ideas here. We have to learn how to utilize Avogadro's number to go between moles and individual items, in this case atoms, and we have to be able to utilize the molar mass of an element to go between grams of that element and moles of that element. Now, of course, all of these ideas can be applied to molecules as well, and compounds, right? So just like a molecule has the formula mass, right, as its equivalent to the atomic mass of an atom, there's also molar masses of a compound, right? And just like we saw with formula mass, right, to get the formula mass, we added up all the atomic masses of the elements. To get to the molar mass of a compound, of course, we're going to simply add up all of the molar masses of the element. And so the molar mass of a compound will end up being numerically equivalent to the formula mass, but simply in different units, right? Grams per mole, right? So the formula mass was in AMUs, right? That's the mass of an individual molecule of that compound, or formula unit. And the molar mass is 1 mole, or 6.022 times 10 to the 23rd, formula units or molecules of that compound. Right? And so if I want to know how much 1 mole of water molecules weighs, right? We know that contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms, right, based on the formula, right? So if one molecule contains 2 hydrogens, a mole of water molecules will contain 2 moles of hydrogen atoms, right, if we were to add them all together. And so to get the mass, I'm going to take 2 times the molar mass of hydrogen, right? 1.01 grams per mole. I'm going to add it. 1 times the molar mass of oxygen, 16.00 grams per mole. If I add all this up again, just like I saw with the formula mass, which was 18.02 AMUs, the molar mass of water is going to be 18.02 grams per mole of water. So applying the same concepts we just did for elements, we can apply them for compounds as well. Now, just like we saw with elements, the molar mass allows me to convert between grams of a compound and moles of that compound. And Avogadro's number would allow me to convert between the number of individual molecules of that compound to how many moles of molecules of that compound I have. So I can use these same 2 conversions to work with molecules of a compound or formula units of a compound as I did to work with atoms of an element. So let's try one example here, and let's look at the number of carbon dioxide molecules in 22.5 grams of carbon dioxide. So first thing we look up is we have to figure out what the molar mass of CO2 is, right? Because first thing I'm going to have to do is to go from grams to moles. So the molar mass of CO2, right, that equals 1 carbon. So 1 times 12.01 grams per mole plus 2 times 16.00 grams per mole gives me 44.01 grams per mole for carbon dioxide, right? That's molar mass. So now I can write out my calculation, and I start with my 22.5 grams of CO2, and now I can convert that into moles, right? Because I know that 1 mole of CO2 is equivalent to 44.01 grams of CO2. Of course, my grams cancel top to bottom, and so if I were to solve this, I would get how many moles of CO2. Now, of course, the question asked me to go all the way to molecules. So I want to know how many individual molecules of CO2 that I have here. So if I want to go from moles into molecules, right, that's where I need Avogadro's number. And so every 1 mole of CO2, right, we need our units to cancel top to bottom, contains 6.022 times 10 to the 23rd molecules of CO2. So again, my moles cancel here in top to bottom. So my only units here are left are molecules of CO2. So if we go through and we do the math, retaining 3 significant figures here based on our original mass, we get 3.08 times 10 to the 23rd CO2 molecules. So, applying all the same ideas that we did with atoms, we can apply them to molecules when we're working with compounds.